Our next form of navigation that we'll look at is active absolute navigation. Remember, in absolute positioning or absolute navigation, we've got some sort of a fixed coordinate system that we localize the robot according to. And it's not based on incremental changes within the environment, it's based on this fixed system. It might be something like latitude, longitude, and altitude, or it might be a certain position in the room given a reference point in the room. And just a reminder, when we talk about pose, we're talking about position and orientation. And we've got GPS techniques and related techniques that are good for position, but not so great for orientation, particularly if we're not moving. Just reminding us for a moment about our relative versus our absolute positioning. In our relative, we're computing a pose based on accumulation of movements over time. One of the problems is that the error accumulates over time as well. In absolute positioning, we've got our computation based on an absolute position at a particular point in time. And so we don't have accumulated error as a result. But typically this is done at a lower resolution than we would in our relative positioning. Now, in absolute positioning, we've got localization from reference points within the environment. And they might be active things like beacons that transmit a signal, light and radio waves or sound or whatever it may be. Or they might be passive beacons that don't transmit anything. They might be environmental features like the horizon, for example. Or they might be things like fiducial markers that we place within the environment. So the active ones, we need to install them at certain locations before we can actually use them. The passive ones, we might need to install them, or they might be recognized and incorporated along the way as we notice landmarks and use those landmarks that are naturally occurring. The best known active positioning technique overall would be GNSS systems, Global Navigation Satellite Systems. GPS is one of these systems, and essentially we have a constellation of satellites transmitting information that we receive on a GPS receiver or GNSS receiver and use that information to localize ourselves, work out where we are. So there are a variety of different GNSS systems around the world. Navstar GPS, although it's the best known one and the American one, isn't the only one. There's the Russian one, GLONASS, the European system Galileo, Beidou, which is a Chinese system, which is currently regionally based but going globally very shortly. And India and Japan also have their own regional satellite navigation systems that are used for navigation. Some receivers and increasingly receivers are coming on the market that can support more than just the standard GPS system, but multiple of these systems, which can guard against outages of one of these particular systems or use the best navigation at any point in time. So, essentially how GPS works, we need an unobstructed line of sight view of 4 or more of the GPS satellites. The GPS satellites will transmit a few things. Firstly, the time that the message was transmitted and the position that the satellite was at that transmission time. And based on this information, the GPS receiver will calculate the distance to each of the satellites and determine a 3D position of latitude, longitude, and altitude of where the GPS receiver is at that point in time. So GPS, Navstar GPS currently has about 32 satellites in a constellation orbiting the Earth. And these satellites have an onboard cesium clock, an atomic clock that keeps very, very accurate time. Now we have a few different sources of error. Things like atmospheric conditions and what's going on in the ionosphere as the signals are sent from the GPS satellites to us. And multipath effects, where we have a signal that's bounced off something else. And clock synchronization between all our different satellites and our receiver. So a few different sources of error. Atmospheric conditions is a very significant one. Previously, before the 90s, we had something also called selective availability, where the significant error could be introduced into, particularly over geographic areas, to stop undesirable use of GPS systems, like in guided missiles and things like that, that were being built without using military GPS. Now this has been turned off by and large, and which has enabled us to have very, very accurate GPS systems. Now a GPS receiver performs all these calculations for localization and gives us a position and typically does this as a character string. And so here's one of the character strings available. There's a few different strings that our GPS receiver can give us, like the GPGGA string and GPGLL string. Those ones will give us extra information like altitude. But this one gives us things like our time when we got our fix, whether we have a fix or whether we don't have a fix, our latitude and longitude, our speed over ground, our heading, our date when we've actually received it, and our magnetic variation, so what sort of declination we need to provide if we're converting from grid north to magnetic north, for example. Now, there's a few problems with GPS systems, and they're these: the accuracy, the jamming and blocking, and spoofing that's able to occur. So let's cover these. Firstly, accuracy. Having turned off selective availability, the current standard states that we should get 7.8 meters of accuracy with a 95% confidence. Realistically, for a horizontal plane, we get significantly better than this, typically less than 3 meters of error. And vertical is not so great based on how we calculate our satellite positions, and this is pretty good for course navigation between waypoints, or if we've got a drone that's flying around, but it's not particularly great for passing through, for example, a doorway, where less than 3 meters, well, still might be a meter or two. Our doorway is only 800 mil wide. We're just not going to fit in very accurately using standard GPS. Military GPS broadcasts on 2 different frequencies, and these 2 different frequencies allow us to, or allow the military to correct for ionosphere. And we can significantly improve performance and accuracy when we're doing this. Another issue is jamming. So GPS signals aren't particularly strong, and so they can be actively jammed or blocked, basically by having a localized transmitter that's transmitting over the top of the GPS signals and allowing and preventing receivers from receiving those correct signals. And we should mention this is completely illegal, but has occurred, and has occurred accidentally as well. So in 2007, one example is that in California, in a harbor, a Navy ship inadvertently jammed GPS signals. All sorts of problems ensued from this, including malfunctioning air traffic control systems, pager systems, around the harbour, boat traffic management systems failed, and even ATMs stopped working because they were using the GPS for time synchronization between the ATMs and the banks. Blocking is a more common issue. So in jamming, we're actively trying to jam a signal by transmitting a signal over the top of the GPS signal. Blocking is where a GPS receiver can't get a clear view of the satellites, or there's significant multipath interference occurring. This is something we encounter all the time. Trying to use GPS inside, for example, or in underground car parks or tall adjoining buildings. Through dense foliage, my GPS often drops out going around those windy roads in the Dandenongs. All sorts of environments that GPS satellites are blocked, and we just don't get a good GPS fix in them. Well, GPS spoofing is another issue. Now, rather than jamming the GPS satellites, which essentially renders them useless, another exploit's to spoof them. So you create a local transmitter and transmit data pretending to be one of those GPS satellites. And essentially you can use that to dictate the position to the GPS receiver and lead it away from where you expect it to be. One example that happened recently was a drone was hijacked by a spoofed GPS signal. And so this was done in an academic environment. It wasn't a military drone, but it was transmitted over the top and was able to control and bring down this particular drone, which was a small quadrotor helicopter. Now we should mention that military GPS is encrypted and civil isn't. And so civil GPS can be spoofed, but military can't. And the drone that was hijacked was using just civil GPS. So there's a few different anti-spoofing measures available to us. One is encrypting them, like the military do, but using an IMU or an INS system alongside the GPS to use that inertial data to see if it lines up with what our GPS is telling us. It might tell us that we're going in the opposite direction to what our GPS is telling us, and in that sort of situation we can expect or suspect that we might be spoofed. Another way we can do it is using AGPS sort of techniques that we'll look at in a moment, where we use other radio signals, and Google actually does this, mapping out Wi-Fi hotspots and cell phone sites in an area. If these aren't matching the area that our GPS is telling us we're in, we might be in for some problems. There's a few different improvements on GPS to improve performance. We've got AGPS and DGPS. And essentially with AGPS, what we're trying to do is significantly improve our cold start time. For a cold start, GPS can be very, very slow. 12.5 minutes to download the complete almanac of satellite information. This is because it's transmitted at a very slow rate, 50 bytes per second. Using AGPS, assisted GPS, we can download our GPS data over the network via the internet rather than via the GPS satellite data that's being sent out. So that can significantly improve our time. That can take seconds rather than minutes. We can also compute things like cell phone towers to localize ourselves within a known area. And so it can speed up our calculations. Rather than thinking we could be anywhere in the world, we know we're within a suburb or a couple of suburbs or something like that. Potentially we can also use those cell phone towers to work out where we are and implement localized ionospheric corrections to improve our GPS accuracy as well. DGPS is the other technique, which reduces our error down from meters down to centimeters. And essentially what we have is a fixed a network of fixed ground reference stations around the world. And those ground reference stations broadcast GPS error based on their location. So in this localized area, your GPS error should be this is how you correct for it. And DGPS receivers can receive this broadcast and correct by the same amount. And correcting by the same amount will significantly improve their accuracy. Now, one application where this is commonly used is in autonomous farm vehicles. For example, autonomous combine harvesters, they'd be pretty well useless if their accuracy was down to only about 3 meters. But if their accuracy with DGPS is in the order of centimeters, and people like John Deere do this thing so routinely, they can go night and day and perform their harvesting operations or seeding operations or whatever needs to be done autonomously. There's a few other different active reference points available to us as well, and we'll go through these briefly. Locator is an Australian system and is basically a ground-based constellation of beacons which are all time synchronized with each other. So rather than being in space, this is something that we can put together on the ground and give us very, very high localization accuracy, sub-centimeter. Now we can use this in areas that we don't get GPS particularly well. In mining underground, we can use it in robotic environments, indoors, and we can get very, very accurate absolute localization over a relatively small geographical area. Mobile phone triangulation is another method. And essentially mobile phone towers and the relative strength of the cell phone towers that we can see from a phone can give us very coarse localization. This can be good for starting up a cold start GPS system, but it can also give us a rough idea of where we are. This can be in the order of dozens of meters for urban environments with very high cell densities, or hundreds of meters for less sparsely serviced areas where we don't see that many cell phone towers. So probably not so useful for navigation, but could improve our cold start time and provide some anti-spoofing measures as well. Another system, an older system, is used for aircraft navigation. Non-directional beacons and instrument landing systems have been widely used both for marine and aircraft instrument-based navigation. Non-directional beacons are beacons that are marked on a map and transmit out, and we can work out the heading of that beacon as we're flying along and use that as a reference point as we're flying along. And instrument landing systems, we have directional antennas and light systems to allow us to work out whether we're in a proper landing envelope, whether we're too far to the left or the right, or too high or too low. So they're active beacons that are transmitting and telling us to correct our course and where we're headed.